Okay, so hello everyone. Thanks for joining today. So we are like semi-final week. We are week 3 now, and later we'll have week 4. I went over the course content for this week. It was more in the concepts that people nowadays are usually aware of. Like I'm not generalizing it, but yeah, and then even the prof he didn't go into much of details there that following the maths of it, but he just explained it like superficially. So I won't be adding up to the mathematics today. If you want, he has said that further he'll share the slide codes as well as the maths for it. So we all can always go over there and look into it. I came up with a like I saw a new source like weeks back, and that was like Notebook LM. So I thought just to give it all of these slides and see if we can get a summarized viewpoint of it. It has done pretty good job there. So I'll just show you. So yeah, following this week, what do we have is we have all about segmentation classification. We start from decision trees, then we go to random forest, then from random forest we have neural networks. From neural networks we have like deep learning and networks. Then it's being taught that okay, how to build our own network. 2 minutes. Yeah, and then based on a single network, how should we optimize the cost function, objective of that function? How do we minimize it so that we get a maximum value there? And what are the metrics to be maintained inside it? So those are like just superficial parts to it. Then he has explained some nodes and leaves over there with some basics into classification, how classification is different from regression. So we'll be looking into it, and I guess let's just share slides and see. If you have further questions, you can always let me know and we can discuss into it. Okay, so now. Yeah, so this is like if you don't know what this is all about, so this is one website called Notebook LM here, and if you just feed in the sources, it won't generate data as ChatGPT. It's not. It's of course it's a large language model also. It's built up from Gemini, but what it does there is it won't generate data on its own. It will generate data from the source that you are providing it to. So it's also a type of problem that we are solving here. That's why I thought let's just introduce this model here. So it has something as trees, and so it is the preliminary model of ChatGPT was also based on simple decision trees, and later it went into convolutional networks and layers, and then hence the large language model that we see today. Yeah, so from all of these large language models that you see, I'll just present my slides. Um, just the shortcuts are not working. Okay, yeah. Yeah, so as for my introduction, I'm Jagriti. I'm a fourth year PhD student at IIT Gandhinagar, soon to be a fifth year student following this summer. Okay, so if you see over here, this is a very nice schematic that this notebook LM made for us, is that everything starts deep from its roots, then it goes and branches off. From the branches, we get different nodes, and eventually we get all of these, which are like final conclusions, which are called as leaf nodes. From this leaf nodes, the field advanced and further went into neural networks, and then which are like here, what you see are something neurons, which are like networks in our body in physiologically what you have. So that's one neuron being represented, but that's essentially not the neuron that we're talking about. So these two are the two different neurons, but it's also one part of process where information is being processed and how fastly it's been going through, hence the representation here. Okay. So we'll just see how machines learn to see the world. Okay. Next. So what's the goal of machine learning is just a simple sense that every algorithm we'll discuss here, everything will have a different mathematical approach, and we have different probabilities for it. These probabilities are nothing but gained through its measures, its performance, how it performs, and then we'll see through its own experience. Now, this experience comes to the errors, the biases, the variances that are being rolled over there. Okay. Yeah. So this was a simple case that professor had in his slides. Was that first, if you take a simple classification problem, now you see all of them, these are like all different. The sizes, the structures might also vary, but in some cases, some geographical conditions, they might look even similar to each other. So you can't tell apart that which one's what. Okay, so there's this simple classification problem that it can you through their visual characteristics, can you differentiate in between them or not? So just consider that you have added a case in between and you have a worker which will help you solve the cases. So it will help you classify them into a part. Okay. Now, how it first goes is, so there are steps to it, and through the OneDrive link that you all receive every day, where the session recordings, you get access to it. There I have a OneDrive folder in which I have added the week 3 lecture notes for this week. So these are like the lecture notes that I make myself whenever I go through the lecture slides. So I've added one by one processes there. So here you had this variable of classifying in between these three folders. Okay, so sorry, not three, but the four types that we are seeing over here. So what goes through them is like, we'll just see processes. So first, we'll just split the data with logic. So these trees operate on a recursive logic. So after each and every branch of layer, they'll again reiterate the process to see if they have minimized the error or not. Okay, but how does the tree know which question to ask first? So there are like steps to it. And these were the steps that Prof also emphasized during the class. If we need to be very particular about it, so the first one is to split the function. Split the function in between two nodes. So you have one main objective. Now you split that particular objective into two nodes that you are just the first question that you're trying to ask into. Then you assess the purity of the split that you want to access. Now the purity of the split would be the probability of that particular split, which you know can be calculated as the number of samples with respect to the total number of present sample cases in that case. Okay. Then you have come out with a cost function. Now this cost function can be anything which helps you minimize the function error and maximize the probability that you're trying to see over there. So in this case, the error that we are looking at through is the entropy. So entropy is nothing but a measure of randomness, impurity, unpredictability in your data in the class distribution. I guess these two terms are repeated here. Yeah. And then information gain. So what does gain? Gain, whenever we look at the higher the maximum is a better. So if the information gain increases, then our entropy reduces at most of the places, saying that this is the most particular decision that our tree has made. So everything is based on probability. In this case, we are talking about conditional probability, not for joint or continuous probability. Okay. The next question comes that, so to like, which is an optimum feature that we're trying to look at. So the optimum split that we're looking at. So for an optimum split, we'll always need that which feature and what the value of feature that you're trying to optimize there. So for that, you'll need some nth feature dimensions to take random natures of it, select random ranges from them, as long as those random ranges fall into your dynamic data range. Okay. When you do that, each and every decision tree will have a major limitation of the complexity ceiling. So how maximum and how in depth it should go. So it should never be always that it becomes too rigid that you cannot go apart from it. And if you have some unseen data or it is not trained on, then the logic that you're trying to test it on will always fail. So there comes a problem that you'll always need to see that where is your stopping criteria in this case. Now, for stopping criteria, what people usually do is like they'll take some thresholds, or the most optimum case that they can do is see where your entropy is minimum, can be like too close to zero or nearby towards zero. So it is negligible where you can consider that my information gain or my or my conditional probability has increased to this nature. Okay. Then there were wise people who then came upon a point that, okay, this decision trees, when you decorrelate them and when you look on them specifically at separate classes, there comes this random forest. Now, random forests will solve the brittleness of each and every single tree by chaining an ensemble. Okay. What here ensemble means is that you are not only going through, so let's just say that I've acquired some images and I've acquired these images at particular time frames. So okay, so I am, let's say I'm imaging I'm imaging blood flow. Okay, so this blood flow at t equals to t0 and t equals to t2 or t3 or t5 would be at different locations, different anatomical places, right? So now I'm acquiring the data at, let's say, delta t time intervals in between each and every successive frames that I'm taking here. This type of imaging can be either ways. It can be either CT, MR, ultrasound, whatsoever you think here. Okay. Now, when I'm doing a stack of these frames are nothing but called as ensembles. Okay. And now I want that my sample to not be only trained or not to only look at the decision tree of one frame, instead look at towards an ensemble of them, so that it will be able to track that where my probability or where my distribution function is moving towards. Okay. So there what we here look at now, it can also be the case that where you don't have enough number of pixels to fit it on, it will give you an overfitted or an underfitted model. So hence the nature of averaging their probabilities altogether towards this ensemble is a point that makes random forest unique and helps it to solve the problem. So we get a collective output of many smaller and slightly different models here. Okay. Here, what you're seeing is nothing but the density functions where your probability density functions are true in this case. So you're just looking at the probability density functions against the frequency and the bins of your data point. So for a particular tree against a variable that you're looking at time, let's say this is your first tree, second tree, third tree, just see that where your frequency is highest amongst, and then you average all of them. Instead, just taking the bin where it was first highest. That will prone to be much more biased and more erroneous data set. So when they do that, it is something which is called as bootstrap aggregating. That is nothing but simple terms, that's backing. Okay. So what that means is that you take a democratic way to decorrelate all the trees that you have. Okay. Now this democratic way is nothing but for each and every tree, you assign equal values. And towards the end, you average all of the probabilities across the entire forest that you have. So not the forest, that is like entire all the trees that we have built on. That simple thing. Now, when you're doing that, one thing that people are giants who built on was to not just take the values as it is. So you have, like, let's say you have multiple features that you're trying to build your tree on. Now they say that shuffle the data set. Don't only shuffle it within one tree, shuffle it across an ensemble of trees so that you'll be able to get. Now, in this case, just imagine that if you have the probability highest for tree one, and now you're shuffling it across, and other trees won't even give you any such data, your error would be lesser and lesser. So, shuffling here does not give you does not bring you on the edge of getting your data more erroneous there. So won't even cause you any changes in your data set. But in this case, it will help you when you're trying to test your data set. Because when you are training your data set in a manner that it is already prone to such edge margin towards cases, then when you are testing it, you'll be able to solve it much more accurately. So your sensitivity, specificity, those values will even be higher in that case. Hence, when you do this bootstrap aggregating, what people do is first case, they randomly subspace the method. So in this case, we're not only talking about the feature random shuffling, but we're talking here about the sample subsets random shuffling. Okay. And then they democratically vote them. So when classifying a new data point for every tree in the forest will calculate a probability, the final prediction is generated by averaging the probabilities across the entire forest. Okay. Then now when you do that, the same thing. So here it's like always coming back to one thing and other thing. So you have done it, you have averaged them through, but then till what point you should do it. So there again, your entropy and information gain again splits into. So raw image pixels, human speech, everything, they do not easily break down into simple just true and false. So you just need a so you need to have a rigid logic to look into biology or to see which particular threshold is wise for me to choose for that particular data set that I'm trying to look into it. Okay. Now, when people were done with this random forest based methods, they thought that, okay, when we are trying to just make different trees based on the observations, the logical findings that we are looking into, we can simply build up a model. Then, based on multiple trees, we can have a decision trees through ensembles, we can train them, look at the average values of them, and hence towards the final conclusion point that we're looking into. Okay. Now here, if I wasn't that much clear, but yeah, these points are what you call nodes. Okay. From the first one, the parent, the root one where it's coming from is called as a parent node. The ones which are splitting into are the child nodes. I should have told this earlier. Sorry. These are the child nodes. And the ones which it is like concluding on, let's say these one are the here, which it is concluding on, are the leaf nodes. Whereas the functions that will be written over here across this edge cases in terms of random forest follow simple logics. Okay. But what it makes it different from this ones is that here we add some weights to the function which will be eventually looking it towards your entire function that you are here evaluating it through. Okay. Now these weights are nothing, and so any particular input value, you'll add some random weight to it, and this weight will be eventually optimized, and you have different functions for its own optimization. Nowadays, Python, MATLAB have their own libraries, and through these libraries, you don't even need to solve them. It will just do some hyperparameter tuning and optimization there, so that you get an optimal weights. Your features are like tuned towards the data that you're trying to looking into. But always need to consider that you have a bias added into there, because whenever you have this inputs and weights, it's always the initial point or the condition is that for zero input you always have zero output. Okay. But for this particular condition to not always get the zero bias, you'll add a bias, and that bias can be unity also. Now, this unity will help you shift your model towards left or right transverse cases. When it does that, it will help your model to tune in a case which is like directly like fitting your data, or will try to see the distribution of your data that it is actually relying on, and not only based on the input weights that you are giving, based on the input sample space that the model is trying to learn from. Okay. Now, when you do that, whenever you get functions from these neuronal based models, you have an activation function. Now, this activation function, the only role this activation function plays over here is that it keeps your data and the final output that you're looking through this like learning based model, is that it is bounded, meaning that it is lying in between two values. It's not like shooting your data values out, and then it is differentiable. What differential here means that like at each and every point of the node where you'll be evaluating your function, always your entropy should be minimized, and you'll get a maximum information gain there. So it is like giving a maxima there. So to for a model to get a local minima, a global maxima, it should be differentiable, be bounded within limits. So if you have learned within your limits and functions, that follows as Bibo rules, input bounded, output bounded, as like that. So you have an input activation function here for the same case. Now this activation function in this case based on our data sets can be linear, can be non-linear. If those are linear, the classification that you're trying to look into would be strictly limited to databases which are following strict bounds. So if I have it here, um, let's see. No, I guess I don't have it. I have it in the notes. Yeah. So how it would be like, let's say it would be either suffice to an axis which is directly perpendicular, sorry, parallel or perpendicular to your origin axis. So your x and y axis, or it can be as it is following a circulic or parabola or a quadratic polynomial like that. So it's always dependent on your data set that which kind of activation function that you're trying to look here into. For basics, people always go into sigmoidal. They go into some, so you might have heard something about ReLU activation functions. So those are something about sigmoidal functions, which will keep your model in between 0 to 1. Apart from that, you have some other functions which are like hyperbolic functions. This hyperbolic functions will ensure that it's from -1 to 1, but you never want negative limits to exist in between your model, because that itself inherits non-linearity. So you always want it to be monotonically increasing, bounded, differentiable function. So let's just ensure that we are always like having the absolute function of this activation function, so that our limits are bounded from 0 to 1. Okay. So everything here that you're looking into is nothing but joint probability now. Now we are not talking about conditional probability. Okay. Now, when we do that, you have different layers. So one single neuron that you looked there was a simple decision that we're looking at, is like that we were taking. Millions of neurons stacked in layers will approximate the function. And now you'll have like input layers, you have different output layers, and within those layers, you have certain hidden layers. These hidden layers are the one where you have different weights applied to your inputs. Can be that you are applying some convolution, correlation in between them, selecting the maximum highest probability function, the lowest entropy like output function, and thereby you give an final output to your function here. Okay. This type of stacking is nothing but unstructured, okay, and it's not even supervised by us. So this is like completely unstructured. You give certain layers. Now what you need to consider in this case is the dimension of the layers that you're trying to insert into. This dimension would be dependent on your size of the data set that you're looking. Now let's say if I'm looking into 8 by 8 bit image. So my size of this input structure would be 256 cross 256, okay, 2 raised to 8. So here we are like just talking into bit set, how many bit dimension that my image would be splitted into. So I'll have that many pixels, and for each pixel, or let's say stack of pixels or kernel of pixels, my model would be trained on them, and later it will try and classify or segment for all those cases, okay. So yeah, my input dimensions are always based on the raw image that I'm looking into, and this everything, how it's falling through in between intermediate steps, it's unstructured. I'm not giving it a specific layer or the dimension that it should always follow through. But the layers that I'll be adding in between, these layers will also have a dimension so that it minimizes, that is, it downsamples it maximizes it, that is, it upsamples it, and towards the end, the output is what your input image was. It can be either be compressed or it can be even be upscaled. So it can be a downsampled version of your input image that you're looking into, or can be even an upscaled function. Okay. Then, like these are cases that you always do. So something has to evaluate the performance. So here you have a cost functions. So how do you know the current weights that you have for a model and where you're stopping it at are correct? So you define a cost function for it. This cost function will aggregate the error. This is nothing but basically minimizing your entropy, maximizing the gain. So same thing that we have learned again and again. So what it will do is like it will look at the network's prediction, the ground truth amongst the entire training data set, and finally it will minimize it through. Now in this case, cost functions that we are looking through can be squared errors, mean squared errors, can be Euclidean distances, can be differences. So there are different cost functions for it, and each and every cost function has its own pros and cons. Why to use one specific cost function is actually very dependent on the type of activation layer that you're selecting through and how you want your data to be minimized. Okay. So nowadays, is like people previously they used to code the cost functions, different layers, and how to minimize these across your intermediate hidden layers. But now, how you do and implement these models as, let's say, random forest or support vector machines or something as the CNNs and DNNs, you don't even need to add anything. There are different, like if we are talking about Python, there are different scipy libraries available into scikit-learn that you'll just have different optimizations there to have your hyperparametric optimizations. Now, what it will do is like it will tell you that which layer is like giving you most minimum entropy. Now, how you should change it, how you should tune it, you just look into library, see which inputs to it to be passed through, and you'll get a minimum function there. So you don't need to even optimize it, or let's say write a function from scratch for this type of cost functions. Whereas the one that we're actually looking now is the simplest one. This is like it follows Euclidean based losses. It will see the probability at where your ground truth was and the probability what your model predicted you for. It will take mean square distances, mean square root differences in between both of them. So that's essentially your Euclidean distance. Okay. And then how it learns from its errors. So this convolutional network based models or this neuron based models are something which have its own feedback. Okay. So what they'll do is like they'll try to minimize, they'll again see that from which particular ground state to which state they have now achieved into, then again they'll try to do the same. Now how this whole loop works is something called as gradient descent. Okay, now this is nothing but a partial derivative of your cost function with respect to your objective weights that you are applying to your input values. Okay, so that will tell us about the slope of the error that we're looking here into. What is happening over here whenever we are going back again assigning the values there, again taking a minimization, again assigning the value, that is something called as back propagation. When you do gradient descent, where you take a sigmoidal based models with back propagation, there are certain errors which it follows. If you want to see those errors, just take your sigmoidal function. That's like your x1 inverse of your 1 plus inverse exponential function. Take that function, take a derivative of that function. Evaluate the function at 0, negative infinity, positive infinity. You'll get a curve of that. Now see where the derivative is finite. It will give you something as Gaussian. When you have those Gaussian functions, right? Now at its let's say the tails that we're looking into, it's limited there. Now your model is not able to define, like it won't be able to go extend towards plus infinity, minus infinity, and it's only stuck on the global maxima. So that's how these techniques are like they're trying to optimize themselves, and the method behind it is called as backpropagation. So here one such example that I gave was for sigmoidal. You can go through one such website as like Geeks for Geeks or Stack info stacks or something like that. There you'll get this like this derivations, and you just write gradient descent for ReLU or for this sigmoidal functions. You'll get those very quickly. Okay. And then these models have been used to see entire unstructured visual data sets. So you just label all of them. It will locate the figures in a frame. It will describe the scenes that you're looking into, some objects that it has like seen through, and will also recognize individuals. So this is like one such example for visual image processing. Then there are examples on medical imaging. So we previously learned that there were differences in between the texture and the statistical features that we are looking into, some structural and statistical features. So what here it does, those statistical features that we looked last time was something based on the tissue specific speckle, right? So at different parts of organs, based on the imaging modality, the speckle will also differentiate. So here what it does, it will see how one speckle of a single pixel matches to another one, and we'll just try and optimize all of them. We'll just try and stack all of them. It's nothing but simple, similar to how we saw the local binary patterns, trying to match in between the nearest neighbors and then stacking them all apart. Now, in this case, we don't need to make vectors by ourselves. The model will do it by itself, and then it will see that at which particular point my error was minimum. It will tell us the uncertainty at that point, and we'll try to differentiate that. Okay, now this layer is different from the layer that is below it, the layer that is next consecutive to it. Okay. So that's how this whole thing came. So first you had the simple logic and rules, the decision trees. We were maximizing information gain, minimizing the entropy, having very structured, interpretable, structured decisions there. Now the final leaf notes for this model were the inferences that you take out from this network. After that, what people came up with that, okay, let's just reduce the bias, the variance that we are getting here. So the uncertainty that we are looking into. So then they went with an ensemble based consensus. So that was like random forest. With random forest, they used this bootstrap based bagging method and then this democratic voting there to overcome the overfitting limits of the logic. But whenever you do this kind of methods, like I myself am very devoted towards physics based models. So I will use these models if at all it's needed, if at all it enhances the study accuracy, or the way it can be near towards clinical translational, or it will like help me to solve big data problems. But in these cases, whenever you do so, do always see plot each and every different individual function, that how it's performing with respect to the inherent data, natural data that you gave it. Because always uncertainty of, let's say, 10 raised to negative 3 or negative 5 won't say that, okay, you have optimized your model, but the fits might be bad there. You always go try, like, plot each and every function, visualize them, see its metrics like R square, RMSE, some structural indices, similarity indexes, evaluate its sensitivity, specificity, look at its area under the curve profile, then only depend as like finally believe or trust what the model is giving you for. Don't do this thing for your entire data set, but let's just say if you have, let's say, 50 samples, you train it on 30 and test on 20 and then see how it's giving you a result. Then only, like, for your, let's say, million based sample data samples, trust on it. Okay. Then you have, let's say, optimization and architecture based problems. So you have like neural networks there. To do all of this, when you are basically doing neural networks, you do need GPU. Whereas still something as like point 0.1 and point 0.2, you can always do it on your hardcore CPUs. But yeah, if you have a 16 GB or higher than that only, it's preferred. Or if not, then go work on a workstation or take some credits from this OL, other Google-based or Gemini-based sources that have been following through. Okay. So with that, I had this much only content. Other content which I haven't written, I have already added those to the OneDrive link. If you have any questions, you can ask me. I had few other questions from the apart from the assignments today. So we'll first go through them and later we'll take the assignment questions. Any doubts? Okay. So I suppose you all are clear on what we just had now. So I'll just start with assignment questions then. Mm. Okay. Yeah, so there we go. Uh, you can unmute yourself whenever you know the answer for it. Uh, okay, so the first one, which metric is used to measure the uncertainty of a class distribution in a node? You can hear me, right?
Yeah, yeah.
Ah, okay. Anyone?
Entropy? I
Yeah, it
mean,
is.
B or D. I was confused between B or D.
B or D. Oh no. So mean squared error is when we are trying to minimize our objective function, the cost function. But when we're trying to measure the uncertainty, it's always the entropy. Okay. Next question. Information gain. So when we form a decision tree, which split is considered most optimum? The one with the lowest cost, one with most number of nodes, like maximum number of nodes, with maximum information gain, or the one that is axis aligned?
Maximum information gain.
Yeah. Okay. Now here there are different split functions. I guess I haven't but I just mentioned them briefly when we were going through. So there are like this split functions like this here. So something as the functions which will be parallel to your x or y axis, something which would be like which will have a slope and intercept or can even pass from origin. And then would be others like polynomial based fitting model. So these are like different split functions. So when we have different split functions with respect to the course content, which one of the following have we not read upon till yet? We had axis aligned polynomial oblique ones. So this one is the only one. Log based. Okay. So when we were defining bagging, What does bagging stand in terms of random forest?
B, bootstrapped
Hmm,
aggregation.
that's that. Okay. So when implementing random forest for a single, what are the advantages of it with respect to a single tree? So yeah, we looked into it, but there are also advantages of random forest with respect to simple regression-based problem, support vector machine-based problems. So that was what there was in the lecture slides. So either you have it resilient to noise or topology independent, simple formulations, lower memory, or faster training on CPU. So you always know it won't be a faster training on CPU
Yeah, I
because
mean
a whole
A.
forest with yeah, yes. So it's resilient to noise because you're always trying to minimize the entropy. You're averaging it throughout. You're doing bagging there. It's topology independent because you're not defining the topology, but it's always the topology is getting divided based on the decisions that you're trying to take and the depth that you have limited it through. Tree decorrelation. So how do you achieve decorrelation in between trees? Or do you use a same split function for every or different trees on different subsets, or by limiting all to a same depth? So here decorrelation essentially means that one is not related to another one. Everything would be trained and tested by shuffling them, if I want to use a different word here.
Option B.
Option D.
B, I think.
B. So B says that you're trying to train every tree on the entire data set. We are not trying to train on the entire data set. Instead, we are taking chunks of our data set. We are also not using the same split function for every tree. We are trying to
I think
train it on
C.
different trees. Yeah, on different random subsets, trying to minimize, shuffle it through so that will towards the end we are on like average it throughout and get a minimum variance or bias there. That's how all our trees are decorrelated. Okay. So this was a neuron equation for a simple neuron model where you have this as your input, this is your weight, and this is your bias. So here everything is written as this, okay. And plus BW bias at ith limits, like this. What does BW represent? Sorry, I just said it. Yeah. What is this term here?
Bias, obviously.
Yeah, that's bias. Oh, what happened? Okay, so when y is neuron, sorry, non-linear activation function like let's say sigmoid or this is I guess tan hyperbolic function, tan something like this, applied to the output of a neuron. So is it to make it faster or to reduce the weights to allow it to represent complex nonlinear patterns or to eliminate the need for backpropagation? Well, backpropagation is always needed there.
I think to reduce, well, no, to allow the number network to represent
Hmm.
complex and nonlinear
Huh.
pattern.
Yes. So it's always because we don't want our data to be restricted towards one specific topology. So that it would be tuned, the weights would be tuned how our data is being presented there. So it will follow nonlinear patterns there. Okay. When training, what's the purpose of the cost function? To measure the error or to define, to store, or to increase the learning rates.
Uh, Purpose of cost function. Increase learning. Measure
Sorry, someone else?
the measure the error between predicted.
Yes. Yes. Don't be doubtful when you're saying something. Be confident.
Yeah,
Yeah.
I'm sorry. I was I didn't read the entire like options. That's why.
Yeah, it's fine. Yeah, so it's to measure the error. So how it we defined it was like something this the probability at each unit minus the second unit. So it can be either defined as your Euclidean distances also. So that was your purpose of the cost function. What's the primary role of back propagation in deep learning? So what back propagation does is that it will use the error, adjust it off, and reiteratively try and minimize it.
See,
Mhm. So it's essentially to calculate the gradients, update the weights, minimize the error. Everything here is done based on gradient descent. So that's like one basic fundamental problem in learning based methods. What's an epoch in the context of gradient descent? I don't know if we talked about it, but it's similar to how an ensemble is being processed.
uh, option B, one complete pass of the
Yes.
entire.
Yes. So that's like a complete pass of an entire training data set to the network that we're looking into. So an epoch can also be termed as a window in a particular time series data that you're trying to evaluate it through, or an ensemble of a frame that you're looking at. Oh, yeah, here. Sorry if my network dropped. Yeah, so it's always recurrent neural networks and this long short sorry, this long short term memory based problems which work on sequential data and time series data.
Uh,
So these are like yes.
can you please differentiate between all the four options? Like, I'm not able to
Yeah,
understand all the four.
sure. So convolutional based networks are like can work on your discrete data points that you're having. Whereas you already know about this recurrent neural networks, they need to have continuous data sets there. So a sequential data which data which is varying with respect to time and similar to this long short-term memory model. So these are similar to these ones. Only cases how it's being behaving or functioning. So in this case, it will function as that let's say I'll give you an example that someone once gave me that I'm trying to solve a problem and then I had this a whole lot of homework given back to me. I have this homework in my mind, but at this stage, I'm only solving one problem. After a point when this problem is solved, I'll forget about it. I'll take another problem to solve. Again, another, again, another. So in this case, my working RAM is only limited towards one problem, but my whole RAM is like, or the memory space that I'm looking into, memory space is being occupied for the entire data set space that I'm solving through. So in this case, it makes it faster to implement a problem that it's being focusing on, but the memory is being conserved as more larger there. So it's some solved as long short term memory based problems. So at a time, it's like designating or particular designated space is only assigned to one problem, whereas the entire space is taken up by the whole data set that you're looking at. Autoencoders are ones which have your which have an architecture of your encoder and decoder here. So here in this case, it is something solving as like it this follows something into as generative learning. So what this does is that this one will make up its own data. Okay, it will try and come up with different generated data from your original data set subsample. It will try and randomize it, will make its own new data sets from it. And then this is the task of the decoder to sort them or discriminate it through. So here also what you're looking at is nothing but discrete pixel level data, but instead not sequential time based data. These belief level networks are the ones which are also part of this recurrent neural networks, but they do not work on continuous data sets. It does need a periodic data sets. It follows a periodogram based methods. So something which has a period of t, but it cannot operate when your this like this assumption of a period is being violated. So hence, for this case, the architecture specifically designed for a sequential and a time series based dataset is the B option. Okay, so this is essentially for sequence based modeling.
Okay.
Okay, so for medical imaging, if we have a denoising autoencoder, so again, denoising is nothing but here the role for this autoencoder or essentially the decoder is to see that where my noise is like lesser or where my low pass filter is performing higher, best in cases. So my image is smoother, it has less noises, it is not sharper. Okay, so for which of the following applications it's being used for? So this organ segmentation we saw previously, like Prof also gave an example for retinal nerve segmentation. It was on random forest based methods. Um, then he told us about this Connect. This Connect was also based on segmentation and like random forest. Predicting the age of an ant, that was something as
Classification.
a regression
Classifier
model.
regression model.
Uh,
So
regression. And then we had this tissue specific OCT learning. So in this cases, where you want to look at the so a speckle for each pixel, how it's being varied from different layers of tissues is what this denoising autoencoder will do. Okay. Okay. So here it's essentially based on the what do you call it? Yeah, texture of it. Next one, which split function type results in boundaries that are strictly perpendicular to the feature axis?
access aligned,
Hmm. That's it. These are axis aligned. These are like, it can be something as this at an angle,
inclined.
yeah, inclined. These are something as quadratic or other order polynomials. Sigmoidal doesn't even fall into it. These are the ones like parallel to x-axis, parallel to y-axis, those ones. Okay. What is the definition for information gain? I didn't go into it, but I suppose if you have saw the lecture slides, you know. So I'll tell you about entropy. Entropy is nothing but negative of summation of probability of a term and
It's
log of
BG.
probability of other term. Yeah, exactly. And this information gain is always when you subtract this entropy from its parent node entropy. So parent node entropy from each and individual child node entropy. So that is what this information gain is, and that's how it maximizes your approach. Okay. So in a regression forest, what does the leaf node or leaf model typically represent? What it is like? So we talked about probabilistic spaces. Just remember, was it a conditional one or a joint one? And how do you represent like differentiate classification versus regression based models here? Again, if you just look into regression, this word itself will give you an answer here.
A probabilistic distribution.
Yeah, continuous probabilistic distribution of the Archer space. so that it will help you predict the future variable that you're looking into. Can be either some random or a new ant that you're looking at. Okay. Okay. What's the key difference on the visual output of classification forest compared to SVM based models? So SVM based models do have very rigid and stiff boundaries. It won't smooth you out for your function. It does not follow something as gradient descent based minimizations. And your classification forest is essentially a random forest or decision trees here.
Forests produce more complex nonlinear decisions.
Hmm. So forests produce more complex, nonlinear decision boundaries which can adapt to islands of dataset, whereas these are the ones which produce more stiffer boundaries, rigid boundaries through which your data is can be at marginal cases won't be able to solve. How is the computational complexity of a forest typically visualized in sources? So our very first or second slide diagram was all about it.
A histogram, showing
Yes.
histograms of the number of things.
Yes. We always look at the probability density functions, and for doing the same, we need to evaluate the histograms with respect to number of nodes and the tree depth of the across the forest. Okay. What's the specific mathematical formula for a sigmoidal nonlinear
Tan
function?
hyperbolic. No,
Sigmoidal.
sigmoidal. Oh, it's in one upon one plus
Hmm.
exponential minus. Yeah,
Yeah. Yes. Okay. In the backpropagation algorithm, what's being minimized?
a cost
Simple
function.
one. Yeah, yes. The cost function is minimized there. It is minimized with respect to Euclidean distance. I guess that's done. So these are the questions that I had extra. Then I'll go for the assignment questions that the prof has that will help you solve this week's assignment. Mm, yeah. So the first question is not at all related. Formula of a so full form of a conference, it's fine. Second one, not a type of convolutional network is also like something
RNN.
that, yeah, even if you don't know, it's fine because here we are not learning about which one's not and which one is it. Yeah, here. Which of the following layers are presented in autoencoders? Do we have a fully connected layers, a convolution layer, or dropout layers? So I'll tell you a hint. Fully connected layers are something in between. Convolution layer also in between. C dropout layers towards output. So when you do autoencoder based
All
methods, you have everything there. ABC. Yeah. In a decision tree, the maximum information gain is used to find what?
maximum.
Why?
No,
Yeah.
optimal
So that
split.
you get an optimal split there. Yes.
Okay.
Because the depth of the tree is defined by entropy. How minimized entropy can you get? And that way you get a maximum information, whereas the optimal split is given through maximum information. The solution, oh, okay, it's fine. The solution representing a deep neural network, it can be obtained by optimization because it's never available, it does not have any analytical solution. You always need to have, or always need to do numerical optimizations there.
Okay.
Okay. Now this one. It's a good question. I do think so. But yeah. What's the size of an output from a convolutional neural network for an input of size? So these are like your number of input channels. And then you have this kernel width. You have 32 such kernels. So this 32 such kernels gives you your output channels. So the convolutional operation is found with a stride of 2, gapping 2 spaces apart, and your padding is 0. You're not adding any additional output there. So what would be your output size? So the formula for it goes as M out, the number of channels for your output, are defined as in minus the width of it plus 2 times the padding divided by the stride plus 1. What would be? So if you look, this is an output channel. So basically these two options are cancelled. You have 32, 32. From here, whatever answer you
Yeah.
get would be a square matrix.
Yeah, so it's C.
9 coming. Yes. Okay. Which of the following does not need handcrafted features as input?
CNN?
Hmm. Because there you're adding weights to the model and these weights are being getting optimized. So you're not changing them yourself. Now this one. Hee hee. So I don't know if it was told in the lecture slides. I didn't go through the last ones, but I just came
Same.
through it. So bands,
I also didn't go through the last lecture. That's why I was not able to understand these bands and everything.
yeah. So here this bands is essentially unit of entropy. So when you're evaluating your entropy in terms of log 10 base 10, it is bands. Then when you are trying to evaluate entropy in terms of log base 2, it is like nats or something. So the units are different there. Just 100. Yeah. So when it's like log base 2, it's bits. So it's always form of information theory. When it's log base t, that's nats based on stats. Whereas it's when base 10, it is bands. The formula that you know how you calculate it.
Log base C,
Okay.
it's what nats.
Nats.
Okay.
Okay. So when you do that, here, since we are evaluating our entropy base 10, hence the unit here is bands. A
Okay.
nice way. These are the weights that we are being given. These weights are nothing but essentially a probability for each of the other entropy. So I'll tell you for one case. So we want to evaluate our entropy at node, let's say 1, n, 1, 2. So here how it's being said is 1 is the node that it's being targeted and 2 is the node where it's coming from. So 2 is the source, whereas 1 is the target, okay, where it will go back to. So like this one, here this is 1, 2. So how we'll calculate it as minus of, for the first one we'll have something as 7 by 8, log of 7 by 8, and something as 1 by 8, and then log of 1 by 8. We'll just calculate it real quick. Yeah, so this gives me as uh, yeah, both will have a minus sign as 0.1643 batch. So if I look in here, is this one or this one or this one for the first case. Now if you do for let's say N14, oh not this one, only B and C can the options here.
N24.
Yeah, and then we look at let's say 14. What is 14, 14, 14 here? Now here, the second one you essentially have as 0. So that would be a pure node because after that point, it's not going ahead. Okay. It's not being splitted ahead. And you have
Okay.
N15, this one. This is also 0. So it's also pure node. It's not splitting ahead. So you have 0, 0, you have 0, 0. Okay. That's nice. Then you have N23. So I guess this one's 2, 3,
Yeah.
most likely. So yeah, it would be like 1 by 5 log base 1 by 5. Sorry, 1 by 5, huh? Log base 1
Yeah.
by 5 minus plus you have something as 4 by 5 and log base 4 by 5. I guess that would be something as this because both of them are same. Okay, 2, 4. 2, 4 is this. So 2, 4 won't be 0. So I guess this one then.
Yeah.
Let's see 2, 5. 2, 5 is 0 because it's also pure node. So that's B option. Is it B? That's B. So like that. This is not needed. Then this one. What's the value of information gain at node this one? So here you need to compute the entropy at this point for this node. So how you compute this as this would be 10 by 30 log of 10 by 30. Always do log 10 here. And then since it's for like three weights that we are looking into times 3 and a minus sign here. Okay.
Okay.
So that's for a parent node. And now we want to evaluate for each of these nodes. So I guess you can do this. For one of the cases, how we do it is would be, let's say, 7 by 15 minus log 7 by 15. Then it would be plus 8 by
8 by
15
15.
log 8 over 15, like this. For this, you
Understood.
calculate this and this. Finally, this minus this one, let's say I, j, and k. Minus I, minus j, and minus k would be your answer.
Okay.
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 Okay, when that's done, then here. The size of the feature set used as input by the random forest is what compared to a decision tree?
Uh, Random forest is big. Same.
Yeah, it's same. Like as the number of nodes that you came upon. So in this case, how they are trying to ask is it should always be lesser, like smaller with respect to it, a decision tree. But
Mhm.
this is like the worst case possible that we are looking into. That in a case where we won't be able to classify or solve in such cases, the feature set that we are looking into would be comparable to the decision tree, n number of trees and the n number of nodes that we'll have. So it's same.
Okay.
Okay. True or false? There exists an analytical solution to an equation representing a neural network. Well, that was just like our first or second question.
Uh,
Do we have an analytical solution for neural networks?
uh, yeah, I think the tan. Oh no.
So we use
No.
those nonlinear functions, right? And we
Mhm.
optimize them numerically.
Okay.
So we never have an analytical functions for these networks.
Okay.
We'll always do it numerical optimization. This thing I guess you can solve now. So
Yes.
information
Yes.
gain at node, let's see where it was,
1 by
1 by
3.
3 e, this one, and
Yeah.
then it's 2, 2, this one. So I'll have two values there. Okay. Entropy at all of the nodes. It's also fine 1, 2, and 3. Those entropies.
Fine.
Then this one, restricted Boltzmann machine. I don't know if we even talked about it, but it's like a part of uh, a belief network, and we also didn't go into it. So we'll see what it is. But here it's like a belief network.
Okay.
Yeah, this is nice. So just tell me what you need to do this. So which nodes will last later will split further. Here CI indicates a number of samples here. So you have like 4, 5, 6, and 7 are the concluding nodes. In this case, these are called as leaf nodes. But from these leaf nodes, which are the ones which will split further? So what do
4,
you
5,
like?
and
What?
7.
Yeah, exactly. 4, 5, and 7. Why?
6 is pure
Because,
node.
yes, so it won't split further in this case.
Yeah.
Nice. Okay, a similar question as we did last time. So this is a tensor input size you have here. Uh, I guess what they're asking us here is number of input channels and the number of output channels. So you already have the input channels here, okay? And then they are saying the convolutional layer with two kernels. You have a size 5 cross 5, output channels for the layer. Operation is done with a stride of 3 and padding of 2. So you already have the answer here. You don't even need to compute anything.
Okay.
So what would be it like? So you have a size, this is your input channel. So that's
Yes,
32. So
32.
option this one and this one, right? And then you have the input layer kernels. The convolution layer network is only split in between two kernels. So you'll only have like two output channels.
2.
Okay. This one. So find the posterior probability of class 1 and class 2 for this forest. So this is like we have a forest, we have 8 trees, classifying 2 points as class 1, class 2. If posterior probability of class 2 for the individual trees are this. So this is only given for class 2. We want to find the probability for 1 and 2 together. So what do we do in this case? This is decision forest, splitting n number of trees, having the concept of posterior probability. We have ensemble averaging. Okay, so you just take the probability and average it out for the n sample cases that you have. The probability that you'll get would be the probability for class 2 here. And the probability for class 1 would be what? 1 minus probability for class 2.
Class 2.
Yes. So here in this case, what we'll do is like 1 over 8 and sum of all of them here. 0.25,
Okay.
0.35 all sums together. 1 minus that would be a probability of the second one. Okay, this one. How are the boundaries of classes when we use SVM based classifiers with respect to the boundaries when we use random forest based classifiers?
Boundaries. S- No.
So SVM based classifiers are always strict. They'll always found something as linear based boundaries. These are stiffer with respect to random forest based ones, which has more smoother because they do something as gradient descent based optimizations or back propagation based methods there. So hence it's harder. Okay. Last one here. For the network shown below, find the cost function for this weights are given to you and the ground truth value for y is given to you. So how do you find the cost function here? You have the value of JW as what? You have the predicted one and minus this y1, the ground truth that you have. Okay, where will you get this predicted one? So you have two functions here, y1 and y2. Okay, so let's just make an equation for the first one. So this y1 would be nothing but passing through this nonlinear function, but it has a function of w11 x1, this first one, which is going here to 1. Then you have x2, and then this w12, plus we have x3 and w13. Okay. Now when we pass it to this entire function, now we haven't even added something else. This one weight is also added. Add all of them, pass it to this nonlinear layer. That means that 1 by 1 plus e raised to minus x of the input that you have. This is nothing but x equals to the value that you'll get. That would be the value for y1. We do similarly for y2. Okay, the other function.
Okay.
Now they are the values for y1 and y2 that you'll get. Let's just say that if you get something as a here and the value as b here. So what was the cost function? How did we evaluate the cost function as? Was mean squared error, right?
Yeah,
So that was like square root of this a minus this one, first one minus 1 whole square plus, let's say, the b value that you get here minus the 0 that you have whole square. Okay, that would be the answer for this question. But do you notice what this is? Like this is a transpose vector as 1, 0. This is another vector that you have. So you essentially multiply them as matrix multiplication. So here
yes.
what you're essentially looking at is that if you have vectors, finally towards the end, you'll end up with a scalar values because you are taking dot product there. And these product dot products are nothing but product in between the input space variable xi and the weight of the variable that you're getting it into, which is towards eventually mapped up towards a nonlinear activation layer function like that. Okay, so that's the gist behind it, that how it comes through. That's all for this week. If you have any further questions, you can let me know. The answers are here itself. You can check them. I'll add the
Yeah.
slides to the OneDrive link.
One thing that I had doubt in the simple neuron model,
Mhm.
what is the role of biases? It's just like initiation weight or something.
Yeah.
I'm
So when a function, regular function starts, no, it's always assuming that when you have zero, it will always give you a zero value. Okay. So
okay.
the bias is added there so that it can confuse your model, will give you a left nature or a right nature to it. So it just added to shift it. It always even adds something towards your bias, but this is just added so that it can be tuned based on the data that you're feeding it into. That's why the bias is added.
Okay. Okay.
Okay, so if you don't have any further questions, thanks for joining today. We'll meet up next week, and then we also have an extra session where we'll have some extra questions that will help you for the exam if you have registered for it. That's it for today, then. Thank you.
Thank you. Thank you so much.
Okay, then bye bye.
Bye. Thank you so much. Bye bye.